All right, so we're going to continue with our focused attention on, first of all, thanks for your patience with this. So we're going to continue with our focused attention on the level set method. We're going to add the missing ingredient to what we've done yesterday. We'll talk about essentially the topic of reinitialization today. Before we get to this, so that's going to be the main theme, I want to talk briefly about a few additional side topics that are pretty obvious, so we're going to spend just a minute. I'll refer to that as a level set toolbox, as in how to compute stuff from a level set function. We'll have that in the slides that we started yesterday. No, that we started this morning, that we'll finish tomorrow. So we'll have all this written details, but I wanted to highlight a couple of things. So first of all, let me find my notes. Yeah, there you go. So once you have your level set function phi of space, you might be interested in computing a volume enclosed in your surface, or you might be interested in computing an area enclosed if you're doing 2D simulations. So to do this, so let's say enclosed area slash volume. The natural expression for the area under the level set would be the integral over your entire computational region of the Heaviside function of your phi, dx dy. And the volume in 3D would be the integral over the entire volume, so that's the entire surface and volume of the Heaviside of dx dy, dz. Where the Heaviside is literally the Heaviside. So our h would go from 0 to 1, as phi goes from phi less than 0 to phi larger than 0. Okay. So if you want to compute, I guess with this definition, we would compute the area on the positive side of the interface. So how do you discretize that? Well, we can spend a second talking about how you would compute a numerical Heaviside, but the idea is it is tricky to discretize something like this. What is much easier is to discretize an equivalent but smoother function like this. So that's what we're going to use instead. So we'll thicken our interface. I'm not trying to suggest that this is the only way you can do that, but this is very much a standard level set way of looking at things. You have a sharp interface, but you're going to say now in order to compute quantities based on this, we're going to need to spread our profile around a little bit. So the calculation here would be 0 if phi is less than minus epsilon. It would be 1 if phi is greater than epsilon. And in between, you would have some smooth connection based on some rapidly varying profile. It's pretty classical to use 1/2 of 1 plus a sine of phi over epsilon. That sets the thickness. Times pi over 2 to make this work. And that's if the absolute value of phi is less or equal to epsilon. All right, so this is just a definition for our thickened Heaviside. Once we have this, we can readily integrate with with good accuracy the resulting area or volume enclosed by our interface. You might say then, what do you choose for epsilon? Classically, so use epsilon is equal to dx over 2 classically. So that's the first piece of information. The second piece of information is something we talked about already, interface normal. The interface normal will directly obtain by taking the gradient of our function. This gradient can be written, for example, in 2D exactly. First of all, it can be written in general as the gradient of phi. We don't want to write in our discretization the assumption that we have a distance function, because discretely it's not going to be necessarily true, and so we'll need to normalize that by the magnitude of the gradient of phi. So for example, in 2D, that's fine. We'll write n is equal to 1 over the square root of phi differentiated with respect to x squared plus phi differentiated with respect to y squared. And then the two components are phi differentiated with respect to x and phi differentiated with respect to y. Okay. Interesting. For this, it is appropriate to use central differencing. There's no particular problem here. You post-processing what should be a smooth field. So it is appropriate to estimate this as phi I plus 1 comma j minus phi I minus 1 comma j over 2 delta x. And same thing for phi y. And that's, I think I showed you that quickly at the end yesterday, so no surprise here. You could be interested in computing the surface area, or in 2D, the line length of interface. Same thing, instead of discretizing a heavy side, this time we'll have to discretize a delta function. Sorry. Surface area is in 3D. Interface length is the equivalent 2D piece of information. So here again, you would have to compute, so if you're interested in surface area, you would have to integrate over the volume a delta let me in fact allow me to do this cleanly. So we've argued already that the volume enclosed in phi larger than 0, this is the integral over our volume, whatever we call that, say omega, of our h of phi d omega. Okay, this is what we just said. Well, now if I want to know the surface area, I need to differentiate this. And so if I want to know the surface area corresponding to phi is equal to 0, well, technically speaking, I need to integrate over the volume the Dirac function of my is magnitude of the gradient of phi. So that's an exact relation. Of course, it's not an easily computable relation discretely, because you never are going to find cells or cell grid points that are exactly at phi is equal to 0, so you have to do something else. So again, we need a numerical delta function. So we'll introduce that as delta sub epsilon, and we'll define it in a way that's discretely consistent with what we did right before. So we had this sign transition from 0 to 1 for our heaviside. We're going to do the same thing. We're going to differentiate that. That's going to give us a 1 over 2 epsilon of 1 plus this time of phi over epsilon times pi. It's going to be if we're with an epsilon. So what? I don't know how this happened. Otherwise 0 if okay, so that's a consistently defined numerical delta function that will look like, instead of being a true distribution function, it will spread out our interface calculation to a few cells such that we can numerically integrate that. And again, epsilon equal dx over 2 is the classical information used here. I think, curvature. I showed you the expression yesterday in the code, but we can spend 2 seconds talking about how we compute it. So curvature kappa, strictly speaking, it's going to be the divergence of our normal vector. Okay, the normal vector, as it becomes normalized, it removes any type of curvature of our profile in the normal direction. It is only aware of the change of orientation of our profile, and as a result, it contains the information we're looking for. So for example, in 2D, this d dx of nx plus d dy of ny, which becomes d dx of, well, a pretty tedious expression to work with. It's going to be a d phi dx over the square root of phi comma x squared plus phi comma y squared, plus the same thing in y, d phi dy of d phi dy normalized by phi comma x squared plus phi comma y squared. So you can carry out the derivation and obtain the expression that we implemented yesterday. In a general sense, in 3D. Another way you can write the expression for the curvature calculation is to say that you're interested in the sum of the three principal components, the sum of the three principal curvatures, which can be obtained any coordinate system of the Hessian phi. That gives me the sum of the three ways in which level set field can curve. We are not, however, interested in the curving of that field in the direction that's aligned with the normal direction. We only care about the tangential curving of the surface, which is the only thing that is the true property of the interface. The third curving is a property of the phi function, which is so we're going to subtract this dot gradient gradient of phi dot n. And that's going to give us really only the two principal curvatures that we care about that are both tangential. Dimensionally, this is not right. It needs to be normalized by the to obtain a dimension of 1 over length. So this falls out of computational geometric argument. There's nothing particularly exciting here. Ultimately, that tells us what the level set informations. However, it should be reasonably clear that the gradient of our level set shows up in most of these expressions. It matters to us what our level set function looks like. Again, if this level set gradient is unity, then good for us. It's great. That means that everything will be well behaved and will look nice. If this is not unity, well, it still really works. We're accounting for what the value of the magnitude of the gradient is, so we can work with a non-unity gradient. We can work with a fairly general level set function. However, we're going to start running into trouble under two limit cases. One of them being if the gradient of phi goes to 0, our level set problem becomes simply ill-posed. In particular, if I have no gradient, how do I distinguish between isosurfaces? That's kind of obvious, but that needs to be said. The other situation is, what if this gradient goes to very large values? Well, same way, that means that it's going to become more and more difficult to distinguish on our mesh our different isosurfaces, and it's going to also mean that it's going to become a difficult function for us to transport. We'll make large numerical errors. So for the ease of transport, we want this gradient to remain reasonable, not too large. And for the accuracy of the identification of the isosurface, we don't want to let this gradient tend to 0 either. So I'll make a note of that here. We need for should not become too large. It will lead to erroneous. This erroneous isosurface identification. By which I mean, if I want to find where phi is equal to 0, but I have no slope, I can't do anything. So we're going to want this to remain close to 1, ideally. However, there is nothing really in what we've done so far that guarantees that. And I have the first case in today's lecture highlights this. So I'm going to show that none of the cases we ran really yesterday showed an enormous departure from a unity gradient for our function. But can I switch to another screen? Yeah. So we'll do that quickly, and then I'll go back to we'll go back to the notes. So all right. Okay, so we are in T7. So in this directory, there's a stagnation case. This is a completely made-up case that just highlights the fact that the kinematics will mess up our local level set gradient. We'll spend just a second on it. Well, a minute on it. We'll have two things. The level set itself, I've initialized not at the circle or anything. It's a simple plane, a simple line. So I'm setting G is equal to the X position on my mesh. My mesh is centered on 0, so I'm going to have the left half of my domain be at the level set value at G less than 0, the right side at G more than 0. Okay, and then the second thing I need to show you is the demo flow thing. Here, again, the flow solver is turned off. The only thing I'll point out is the velocity I've set up. U is equal to X, V is equal to minus Y. What is this? If U is equal to X and V is equal to minus Y, does that take it? Now, it's not rotational. This is a stagnation flow. Okay? So I've chosen one flow such that its kinematics highlights the problem that that I want to highlight. An alternative way to show you what I want to show you would be to place an interface in turbulence, where we have locally vorticity and stagnation flows, but I didn't feel like computing a stagnation flow. Computing a turbulent flow. So let me show you quickly how this looks. There's nothing, we really don't need to spend any serious time on this. We're gonna, wait, no, I wanted to open. We're gonna look at this flow. This flow quickly should just be, like I said, a stagnation flow. So if I create a cut at k is equal to 1, I can show you a vector field of this. I will show only 10%, and I will color this by U. Okay? So this is a stagnation flow. This flow will compress the X dimension and stretch will compress the Y dimension and stretch the X dimension. We've placed an interface in this direction in this. So let me go back to the initial condition, and I will add to this an isosurface. Well, no, in fact, I'll color by the G field. So this is my distance field, and I'll show the corresponding isosurface at G is equal to 0. There we go. And I'll, oh yeah, that doesn't work for some reason. So I'll show it in black. There you go. So now as we time integrate this, what happens? Well, our stagnation flow is going to be stretching in X constantly. As a result, our gradient is going to decrease. And as a result, we're going to be flattening out our program until it becomes constant. So concretely, what I'll show is we'll do an elevated surface. But not of the velocity, but of G. No offset. And I'm going to scale it up a bit for this gradient to become obvious. Okay, so this is our initial unity gradient. And because of our flow field, what are we doing? We're flattening it out until ultimately we start being unable, let me kill this here, or hide it. We start being unable to accurately compute where the interface is located. Right? We can't even extract an isosurface of this. Why can't we extract an isosurface? Well, we don't have a gradient. If we don't have a gradient, we can't possibly figure out the location of the isosurface. So the point here is if you are, depending on your local flow conditions, and I guess for the sake of the exercise, we can flip our interface. So if I go back up here and create a plane that's aligned in the other direction, so y of j, I can rerun this. And do the same exercise, but this time in the direction of compression of my level set. And now the opposite situation is going to happen. We'll keep increasing the gradient until this thing becomes unstable. So we'll do the same thing. I'll show you the initial condition, right? So I flip the orientation of the interface. Let me show the elevated surface again. So this elevated surface now, I'm going to plot it with a different scaling to minimize the appearance of its gradient. There you go. So this is our initial unity gradient function. As I time integrate this, what happens? You'll notice, first of all, that I don't tilt the entire thing. Why is that? Because now I have incoming flow from the boundaries, and now my my Neumann condition is not capable of getting the full response from my interface. So, but still locally, what I see is exactly what you would expect. I'm forming, as time goes by, as large of a gradient as my transport scheme allows. And in this case, my transport scheme, if you remember, is an upwinded quick scheme, which has some amount of upwind bias, therefore it has some numerical dissipation, and as a result, it still behaves reasonably well in the presence of very large gradients, but still, you can see that we start seeing oscillations now. I don't know how obvious it is that this is overshooting, but anyway, the upshot here is large gradients are going to become unstable. Our transport scheme will struggle. We'll see oscillations. Small gradients, we can't localize our interface. So we need to fix that, and we'll talk about the method to fix that. Any questions on this, or can I switch back to the iPad? All good? Okay, so let me switch back. There we go. So how do we fix this? Well, we fix this by solving an extra equation. That's unfortunate, but we're going to increase significantly the cost of our reinitialization of our scheme by acknowledging the fact that we need to spend some time to reset the gradient of the profile, the gradient of our level set function with some regularity. So we looked at the examples. Now, the next step is to talk about how to control magnitude of gradient of phi. The answer to that question is in one word. It's called reinitialization. The reinitialization is, the name comes from the fact that the initialization of the level set was the fact that we created this level set as a distance function. Reinitializing it is just resetting it to be again a distance function. So let me find my notes. There we go. So the reference for this, we're going to go back to the in our discussion here. Smerica and Osher, JCP from 94 or 1994 that we talked I listed yesterday. The second one will be a paper that's included in your course pack for today, which is GS and Pang, the entitled Weighted ENO Schemes for Jacobi equations. Oh no, I don't think I included the next one, sorry. That's a journal. It's a Journal of Scientific Computing paper, issue 21, pages 21, 26, and that dates back to 2000. Reference at this time is included in your I think I included no, never mind. This is the two things I wanted. So we're going to talk about this reinitialization. So how does it work? So phi function implies that the magnitude of the gradient of phi is equal to 1. So we're going to put together an equation upon reaching steady state guarantees that. So we'll go from there to 1 minus magnitude of the gradient of phi is equal to 0. And then we'll add a time derivative to this. So to transform that into a PDE, we will essentially say, let us write a time evolution equation for phi. It cannot possibly be solved in physical time because we're solving an extra equation that's not tied to the physics. So we're going to introduce a pseudo-time tau. And in this pseudo-time tau, we're going to integrate an equation that has as a simple right-hand side this. So it should be clear that once I reach steady state, and this goes to 0, the desired property that I want here will be satisfied. That is not quite enough. I'll need to add one more term to this in order for this to work, because so far, if you pay attention to this, there is nothing in what we wrote here, here, and here that tells us that we have a signed distance function. In fact, here we're describing a distance function from an interface, but there's nothing that says that the sign should flip. And so we can equally work with a positive or a negative phi value. To reintroduce the sign, we're going to have a multiplicative coefficient here that tells us on which side of the interface we are. And so we'll write this as a signed function S of phi. There's going to be one extra subtlety. We want our reinitialization to modify the slope of the profile. We desperately need it to not change the location of the interface. If it moves the interface, then it means that it will compete with transport. We don't want, this is an extra equation we're adding. It is fine for us to modify the level set away from the phi is equal to 0 location because it is meaningless at those locations. But at the phi is equal to 0 location, this is where we want our interface, this is our interface. It's obtained from solving material transport. We don't want this to be modified willy-nilly by an extra equation. So we're going to tie the sign distance function to our starting, I'm going to put here a 0, sub-0, to our starting level set profile. So we're going to take our level set profile, we're going to say that that level set profile has deformed and needs to be reset. We need to make sure that it's again like a distance function. But we're going to say that we trust its sign. So we trust the location of the 0 interface, and we trust the fact on one side the value is positive, and on the other side the value is negative. So we'll use it in order to guide us in terms of setting up the distance, setting up the sign. And we will keep this sign, and we'll use this constant, the equation there. So what I'm trying to say here with the 0 is that this is kept constant as tau increases. All right. So let's define a few of those things. So first of all, this is our equation. So we'll spend a little while now with that nice looking equation. This equation is a family of the so-called Hamilton-Jacobi equations. The Hamilton-Jacobi equations are equations that contain the right-hand side that is some non-trivial function of the derivative of the function for which you're solving. So that's the general class of, so let me write this Hamilton-Jacobi. So this is Hamilton-Jacobi equation. So equations of the form df dt is equal to some general function of the gradient of f. This is the general class of Hamilton-Jacobi equations. Okay, let's be a bit more explicit about a few things. First of all, why do we need the sign? Well, we need the sign to help us control the flow, the direction of the flow of information. So let me sketch this in a more concrete way here. If this is x, what we have, so imagine a very simple solution. A very simple situation where this is your profile. We want the exact solution to be, we want solution at the end of the time integration to be this, to be a perfectly unity gradient. So this is our solution, meaning d phi dx is equal to unity. Now, this blue line here is characterized by the fact that d phi dx is larger than 1. Okay? And so we'll want this profile to go to a lower gradient by the solution of this equation. But we want to do that in a way that maintains the sign on both sides. And so we want to make sure that the way we send the information starts from the 0 location and moves outwards from here, such that the sign is maintained the same, and moves outward for here. So we will control the direction of the flow of information that way. So the information output, if you will, will be like this. This is the direction of information transport. So that's what sets the direction of information transport. We can look at one other example. Like this. In this case, d phi dx is less than 1. And so we want this guy to go back up here, this guy to go back down here, but in a way that cascades away from the interface. The way we're going to control this is by setting our sign distance, our sign function. As follows. S of phi, well, we just said phi naught. And I'll explicitly say what phi naught is in a second. Will be positive if phi is positive. That means that by definition we want information to move in plus x if phi is positive, so that information moves up this profile and the sign is not messed up. And we want information to move in down x, so in negative x when phi is negative, so that again we radially send our information outward from the interface. So we will set this sign to +1 if phi naught is larger than 0, and -1 if phi naught is less than 0. And that's important. At the same time, so now you can ask yourself, well, what do I do with the sign at the interface if phi is equal to 0? Well, if phi is equal to 0, I don't want to touch my function. I absolutely do not want to have this extra equation again modify the phi value, because any change to the phi value would then mean moving the location of the interface. But my interface I obtain from a proper physical transport equation, so any extra change to it will degrade the quality of my answer. So I will set the sign to 0 if phi naught is equal to 0. You might observe from this that the likelihood of finding a point where phi naught is exactly 0 is 0. So we need to have something a bit smaller. Like we've done before, we will have to smooth this discontinuous function. So we will have to represent this using a more amenable representation. The representation of Pang and Pang et al. In their paper is the following. So this is numerically more convenient form is the following. We're going to say that S of phi naught is going to be equal. Well, how do I get a function that goes from -1 to +1 depending on the sign? Well, you set it to phi over the magnitude of phi. Right? That gives us that automatically, which you can write as phi over the square root of phi squared. Now, if phi is 0, this is not defined, so we need to fix that. You fix that by adding an epsilon to the denominator. Well, for consistency, an epsilon squared. So the resulting equation we're going to use is going to be exactly that. We're going to parameterize this with a thickness. We will then compute phi naught over the square root of phi naught squared plus epsilon squared. So I've been using this phi naught for a while. The idea of this phi naught is simple. Phi naught is equal to phi of x at t. This is the initial condition. So that's also my phi of x at tau is equal to 0, where tau is my pseudo time that I'm going to use to fix my gradient. Does that make sense? What I'm saying here is essentially a conductor time step. I get a new function, phi at my new time. My phi doesn't look like I want it to look, so I'm going to need to fix that. I'm going to take this phi and put it in this new PDE. And this phi is my initial condition for this new PDE. I'm going to call it phi naught. And then I'm going to time integrate this new PDE. And that phi is going to change as it responds, but my sign is not going to respond. It will stick to this function I started from. All right. Let's bring all this together. The summary is that we solve d phi d tau is equal to an s epsilon of phi naught times 1 minus the square root of d phi dx squared plus d phi dy squared. That's our final equation. I'll point out this is nonlinear. It is still a function that has that performs. There's information transport in this equation, so it has some hyperbolic characteristics to it. It doesn't contain anything that looks like a diffusion term in it. So the stability of that equation is going to be problematic in a number of respects. In fact, it's going to be very similar to the level set transport equation. The stability of this will require some systematic upwind bias. Now the question is, how do you upwind bias something like this? It is not particularly straightforward to know what is the proper way of upwinding that by just looking at it. And that's why over the years people like Osher and Peng and Sussman, who are not physicists, they're not fluid mechanicians, they are fundamentally applied mathematicians. That's the reason why they've been interested in those questions. Because those class of equations, this general class of Hamilton-Jacobi equations, they are interesting and pretty tricky equations to discretize in a stable manner. So we're now going to switch to a solution that was provided by Sussman for the discretization, the stable discretization of this. So I'll say ask applied mathematician. The one that will answer for us here is Mark Sussman at University of Florida. This is an answer he provided, I think, in his PhD. So the approach is going to be as follows. We have to rely on the so-called Godunov approach for computing the gradient. That will essentially share similarities to what we've talked about yesterday. We'll compute, if you will, upwinded and downwinded gradients, and then we'll look at which one maximize or minimize, which discretization maximizes or minimizes the gradient. And then depending on which direction of information transport we're in, basically depending on the sign, we'll pick one or the other. So there's going to be a lot of max and min, so I'll just write out everything in 2D. It's going to be reasonably, I think, reasonably easy to digest. So I'll start with d phi d tau. We need some discretization for that at location ij time n. What Sussman has for this is a simple third order Runge-Kutta. There's an entire class of so-called TVD Runge-Kutta schemes that are obtained by convex combinations of first order forward Euler steps. So this is obtained from a TVD version of RK3. Those TVD RK3 schemes are, they come out of Schu's group. And the idea is that they're convex combinations of forward Euler steps. That's what Sussman uses. I'll say, but for us, we're simply going to do, if you will, TVD-RK1, which means forward Euler. So that's what I have in your code. I bring the right hand side here, so I'm going to have S epsilon of phi naught. Let me put the naught up there, this way I can put the ij below. And now I'm going to have to compute my so-called flux function, the right hand side function. We're going to have a good enough base calculation of this. I'll call that g of phi sub ij. And now let's make it explicit what this g of phi of ij is. So there's no need to be scared, but we're going to need a big bracket. We're computing the square root of the sum of the square of the x derivative and the square of the y derivative. So we're going to need to compute the x derivative. The x derivative, we're going to have two ways of computing it, and we'll take the max of the two. So we'll take the max of something I'm going to call a plus squared and something I'm going to call b minus squared. And then for the y derivative, we'll take similarly the max of two ways of computing the derivative, the c plus squared and the d minus squared. And then we have a minus 1, right? So I shouldn't forget this is the difference between 1 and the magnitude of the gradient. So we're going to do this if we're on the positive sign. So if phi of ij naught is larger than 0. So if the flow of information is in the positive x direction, we're going to do that. Else, if we're in the negative x direction, or negative y similarly, we're going to use another discretization that will look very similar. It will just flip the plus and minuses. We're going to use the a minus discretization squared and the b plus discretization squared for the x derivative. And same way we're going to do the c minus squared and the d plus squared, the max of these two, for the y derivative. Okay? And then finally, if we're at essentially at the location for any reason, if we're lucky, then we don't want any right hand side. We want to stick to a 0 value. So now I need to define what plus and minus is, and I need to define what A, B, C, and D are. So first, let us define A. A will be an upwinded, if you will, calculation of d phi dx. So I'm going to put a minus here to suggest that we're taking points from the left. So this is going to be with upwind bias. Or really upwind suggests the direction of flow. We don't have a flow, so I shouldn't say upwind. It would be more appropriate to say a left bias. Okay, so it's it would be a more descriptive way of talking about it. And B is going to be, well, the corresponding one, so it's going to be d phi dx, but this time the plus version, so the one that's shifted to the right. This is for x. Exactly the same thing is going to be used for the y derivative. So we're going to have d phi dy. We're going to have the minus, and we're going to have the plus. So this is with bottom bias, and this is with top bias. Okay. So I'm not trying to make things confusing, but now I'm realizing that I'm going to be using plus and minus twice, which is not the most clear thing. So I need to, well, I don't know how clear it is, but this is really, this minus here really just means biased to smaller values and this biased to larger values of our stencil. We still have to define what it means. You know, this is just the definition of A. I need to define what A plus and A plus and A minus is. So let's do that now with this. Now define A plus as the maximum of A comma 0. So it's only the positive part of it. And A minus as the minimum of A comma 0. So it's only going to be the negative part of it. Okay, so at this point we have defined pretty much everything. Except one thing. I haven't said how I'm discretizing those guys. I suggested that I was upwinding or downwinding based on plus or minus, but I haven't told you exactly how this is done. Sussman, for example, uses a scheme called a fifth order Wiener. That you would write we know 5. So we'll talk about what that is as soon as we're done here. And so we'll need to introduce briefly the concept of essentially non-oscillatory schemes, and then the concept of weighted essentially non-oscillatory schemes. And in this way, we're going to be able then to collect all this. But you can see that this is not, you know, we started from this simple observation, it would be nice to reset our distance, but the conclusion that we get to is, well, applied mathematicians tell us, they tell us it's not that easy to do. Okay, so we'll compute an upwinded, a downwinded derivative in x and y, then we'll take only the positive or only the negative part of it, and then depending on the direction of the flow of information, we'll take either one or the other, and then we square them up, take the square root, subtract 1, and we have a good enough flux function. Does it make sense to everyone? See how you can repackage all this into an algorithm? Okay, so let's finish with some comments on the time integration, and then we'll talk about we know for a little while. So, what do we need to define? We need to define also sum epsilon. So that's again from Sussman. Right, so how we define the thickness of our sine function. And also Sussman chooses his time step size as being a 10th of dx. And then you decide how many iterations you need to do. So you can integrate this until some time. So then iterate until, well, you would say until some magnitude of the gradient, of the time derivative, some measure of the magnitude of this, so it could be an L infinity or an L1 norm, until this becomes less than some small delta. So while you still have temporal changes, keep integrating. So the idea here would be to reach steady state. It takes a long time to reach steady state. What Sussman did to speed up the process, again, I'll refer to him directly. He uses some stopping criterion that is E is equal to the sum for all cells that have a value of phi, ij, an absolute value less than some reference. So for all cells that have a distance that is not unreasonably large, meaning cells that are close enough from the interface of interest, then is looking at the magnitude of the change between n plus 1 and n, normalized by the number of points in that ensemble. And once this becomes less than delta tau times delta x squared, he stops. And so in this, you need to pick alpha. What is this alpha? Alpha is some distance that tells you whether you're close enough to be to really want to be converged, or whether you maybe don't care anymore about the behavior of the method. And so you could pick a value here that might be 5 or 10 times delta x. Something like that. So within a fixed number of cells times the size of the cell, basically for all points that have a distance that is less than n times the size of a cell, you you need to ensure convergence. After that, you're done. So if you do this, you find that, in fact, the characteristic time scale at which the information flows here is, in fact, delta x. So that means you need to integrate for a delta t that is equal to delta x in order to have updated your front at a distance delta x away from your initial interface location. So if you want to update, to reinitialize properly about 10 times delta x away from your initial front location, you need to run approximately a total integration time of 10 times delta x. With Sussman's approach, you're integrating at a rate of 1/10 of delta x per time step, which means that you would need 100 time steps of integration to potentially reach that criterion. So now think about what we're saying. We were all happy solving a simple linear transport equation for the level set. That's one step per time step. Everything is fine. It goes well. Now we're saying, yeah, but by the way, you'll need to reset your level set function by integrating 100 time steps of yet another equation that ends up being more expensive. You know, look at all this stuff. That ends up being more expensive to solve in order to make sure that your function doesn't go crazy at in the meantime. So we've just suddenly argued that the level set is in fact 100 times or probably more, more expensive than what we were playing with yesterday. So that should dampen your enthusiasm a little bit. It's not that easy of a method to use. In practice, that's too much. In practice, what's observed is that you really want to keep in check the magnitude of the gradient. You don't need for the magnitude of the gradient to converge back to 1 accurately. So this is overkill. It's appropriate if you want to solve the Hamilton-Jacobi equation, which is what Sussman was working on. If your interest is in maintaining a reasonable magnitude of the gradient of G, you can probably get away by enforcing some sort of a stopping criterion based on the number of iterations only. So let me summarize this by saying, if you say 5 times dx at that rate, that means that Sussman would need approximately 50 steps of reinit equation, of reinitialization equation, which is very expensive. So I'll note that in practice, we find that order of, say, 2 to 10, say, steps is sufficient. So it is reasonable as a stopping criterion to not look at the convergence of the method, but instead just look at what is a reasonable amount of work that you're willing to expend on this method. Okay, any questions on what we wrote here? So who here is already intimately familiar with we know? Okay. So we're going to talk about we know because this is an important component. So it is possible, so people who've done quite a bit of compressible flows, they've been exposed usually to CFD for compressible flows, they've been exposed to we know schemes because they're pretty much the de facto standard for finite difference approaches in compressible CFD. If you haven't done a lot of that, then it's unlikely you would have really encountered we know schemes. So we'll talk about we know schemes for a little while. This is again, this is a very practical tool to know about. So let me jump to this right here. So all this is fine, we just didn't discuss how we discretize our gradients. Now at this point we're computing a gradient. I'll show you, so in the code that we'll look at next, the first thing I did is I wrote up, like in 4 lines, the discretization of that PDE using a centered gradient calculation. We can run it, it will take 2 seconds, everything blows up right away. Right? It's highly unstable. So we need to spend the time to implement something a little bit more involved. So let's talk about this. So the topic now is going to be how to compute a level set gradient. By the way, I want to point out, there's nothing that so we already computed this level set gradient using central differencing with no problem when we wanted to get the normal. This is fine. But note that we don't do anything with that normal. At least so far we haven't done anything with that normal. We haven't used it in the right-hand side of a PDE, of a PDE that we were integrating. So we were not concerned about the way the normal was calculated. The only thing that mattered was the accuracy of the calculation. But the stability of that calculation combined with the time integration was, never came in the picture. So we're first going to talk about ENO. Any more people knowing about, who know about ENO than we know? No, nothing more. Okay. So ENO schemes take us back to yet another few applied mathematicians. One of them is Shu again. Oh, well, first of all, let me define the acronym. The idea is that if you solve any type of d phi dt is equal to minus a d phi dx equation, like our level set transport equation, for example, if you solve that equation naively using centered schemes, if you don't have a good handle of the amount of diffusion required, this will be your solution. So say this is, you're transporting a step function like this. As a function of x, say this is your phi. This is your exact solution. A naive discretization will give you that. So this would be a naive finite difference discretization. Why is that? Because again, we require some sort of a pointed bias in our solution. We need some methodology by which we introduce a sufficient number of numerical diffusion, or else dispersion errors will lead to accumulation of oscillations. So we observe the dispersion errors can destroy a solution. Of a hyperbolic problem. And then the question is how to minimize dispersive errors by choosing optimally our discretization stencil. This is the key question at the start of this of the discussion. What is the stencil that you should use to discretize your equation in order to minimize this amount of dispersive errors? And so the idea is simple. The idea, did I? No, I didn't write. So ENO stands for essentially non-oscillatory schemes. The only truly, absolutely non-oscillatory scheme, well, that's not quite true, but almost, is first order upwind. The quick scheme we introduced, I think we saw that in one of the cases when we were computing the curvature. The quick scheme we used for hyperbolic level set transport, it was already oscillating. But quick was still good enough for our purpose. But we need a scheme that has some non-oscillatory behavior, that has some control over the dispersive errors leading to oscillations. The only truly non-oscillatory scheme is first order upwind. It sucks. We don't want to use first order upwind, obviously. It's not good enough. So we want to go beyond. We want to go high order accurate while still maintaining non-oscillatory behavior. Well, we don't know how to do this. However, we know how to do something that's not absolutely non-oscillatory, but that's essentially non-oscillatory. It will essentially not oscillate in most instances. It will a little bit in some instances. Will have reasonably provable properties regarding the amount of fluctuations. So that's the idea of that's the concept of ENO. What is the idea behind it? Simple. It is to build a stencil based on the local smoothness of our data. And all this weird thing here, 20, 62, 53. It's an ICAS report. You can find it online if you're interested. It summarizes everything we're going to talk about. I'm sorry, we're going to summarize the content of this report. Okay, so let's explain ENO, and then from that we'll jump to WeNo. We're going to think about the purely finite difference approach. We're interested right now in computing at that location, at cell I, at a cell center I, we want to know what is the gradient of our level set function. Okay? We want to know, in particular, from the algorithm we've described before, we would want to know what is the value of d phi dx or d phi dy at that cell center. So we're going to start at I, And the process is going to be the following. We're going to add points either to the left or to the right based on the amount of variation between our own cell and the cell to the left or to the right. So that's a simple process. We add either to our stencil point I plus 1 or point I minus 1, depending on which one has smoother data. So the way to think about this is the following. Our stencil initially says only this. Point I has to be part of our stencil. Now we're going to grow the stencil by 1 point. Are we going to grow left or are we going to grow right? Well, we'll decide whether we grow left or grow right by looking at which one of those pairs has the least difference between their values. So the approach is going to be if the magnitude of, so we're working with phis, or yeah, we're working with phis. So if the magnitude of phi I plus 1 minus phi I is less than the magnitude of phi I minus phi I minus 1, then we're going to add as an extra point, as a second point in our stencil, we're going to add point I plus 1. However, if the magnitude of the variation between I plus 1 and I is larger than that between point I and point I minus 1, then we're going to do the opposite and we're going to extend our stencil in direction I minus 1. Okay, it's a simple idea. It's easy to do. Things are going to become rapidly more complicated, so we'll simplify things a bit by introducing a shorthand notation. We'll introduce a delta plus. That's going to be a difference between a pair of points. If I'm interested in delta plus at I, it's going to be the difference between phi I plus 1 and phi I. And the same way, delta minus at I is going to be the difference between phi I and phi I minus 1. So, at this point, let's imagine that for whatever reason, so assume, let's continue, assume that the left direction was smoother. So we're going to assume that the variation delta plus delta plus of phi sub I is larger than the delta minus of phi sub I. And as a result, at this point we've made our choice. We add point I minus 1 to our stencil. So at this stage, we know that point I and point I minus 1 are part of our stencil. So I'll add to this, I'll add this, this red dot here. So at this point, this is our stencil. Now, remember, what are we trying to do? We're trying to compute a gradient. Well, if I have only one value, my stencil has 1 point, I can't compute a gradient. If I have 2 points, what point? I can now compute a second order. Go say third order accurate to match our quick scheme that we used yesterday. I need to add a total of 4 points. I need an ensemble of 4 points in my stencil. So far I have chosen my second. Let's now choose a third. Well, the story is going to be exactly the same. We're going to add to our stencil either I minus 2 or still a possible contender I plus 1, depending on which one adds a smoother data set. the way to check smoothness now becomes less well defined. As I add more and more points, what do I compare with what? Well, what we're going to do is just combine those differences with one another. So essentially we'll say that at this point we've chosen that our reference variation is delta minus of phi sub I. This is our reference variation. Well, let's look at how much that quantity varies between the two potential stencils. So this is now the way we're going to compare this. We're going to say if, and now I'm going to use my shorthand, if the delta plus variation of this delta minus, right, this is what we chose here. This delta minus is what we ended up picking right here. If the plus variation of the minus variation that we had chosen already is less than the minus variation of that minus variation we had already, then I will extend the stencil on the right. Else if the plus variation of my current variation and the minus variation of the minus variation, then I take I minus 2 as an extra point. Okay, so this is now our reference quantity. This is what we're working with. We're going to look at whether whether that quantity varies more if I extend my stencil to the left or if I extend the stencil to the right. Those are operations that combine with one another, okay? So now based on the answer, I can pick one or the other. That will give me a third point. And then I need to go through this once more. We're going to stop here, but depending on the outcome of this, you'll have 3 points. Then you do this one more time, so you'll have a delta of delta of delta. And then you'll pick your fourth point. Once you have your fourth point, you have a third order ENO scheme. If we were to stop here, after we've decided which point to add, we would have a second order ENO scheme. So I'll just say keep on adding stencil points up to the desired order of accuracy. So 1 point is obviously useless for a gradient. 2 points, this is essentially an ENO1. This is either pure upwind or pure downwind. 3 points in your stencil, this is an ENO2. 4 points, that takes us into to a third order accurate scheme, an ENO3. By the way, we're not quite done here. What we have at the outcome of this is just the points that we want to use. You still have to provide the discretization for the gradient, but for that, we're doing finite differences. You know the stencil, and you know where you want a gradient. You can use simple Taylor tables. You use the Taylor series. You obtain the discrete form. So with stencil, form the so-called Taylor table and obtain coefficients. All right, does that make sense? So this is ENO. I'll add to this a comment, and that's a big deal. The only thing we've considered so far in playing with this is the smoothness. The smoothness is not all that matters. Typically, again, the idea of an upwind bias matters. All right, so you're not free to choose any discretization you want. You might need to choose an upwind biased or a downwind biased discretization based on the flow of information. So we actually need to do a bit more here. So we need to consider more than just smoothness of the data. And in particular, stability will typically require an upwind bias. That might mean that, yes, the 5 points to the right are the smoothest, and we always want to use them in order to use the smoothest data. But they might just be out of reach because we systematically need to have some sort of upwind bias, and therefore we need to, if the information goes from left to right, we need to have points from the left in our stencil. So we need to balance those two things together. So that means that there's one more level of complexity. Ready for it? So let's do a full example of a third order ENO for a linear equation. So if I'm interested in solving d phi dt plus a d phi dx is equal to 0, I'm back to the original problem. If I say that a is larger than 0, then I will need to upwind my data and left bias my information. If I want a third order, that means I need 4 stencil points to calculate d phi dx. I need also an upwind bias. Well, you could argue that a set of 4 points that contain some information coming from the left, there's multiple ways of defining that. So, in fact, I would argue that there are 3 stencils that are possible. Stencil S0. This is I minus 3, I minus 2, I minus 1, I plus 1, and I'll need I plus 2. So you could do that point, that point, that point, and that point. This is a set of 4 points that are as upwinded, have as much upwind bias as possible. And for this, I'll give you one example. We're not going to go through all of them, but this is something that will give you a discretization that would look like d phi dx at location I, upwind biased, stencil option number 0. That would be a 1 over delta x. And you would write this as a delta plus, right? We're going to use still the same shorthand notation, times phi sub I minus, I minus 3 over 3 minus 7 delta plus phi sub I minus 2 over 6 plus 11 delta plus phi sub I minus 1 over 6. This is the corresponding discretization. You build your Taylor table, you find those coefficients. It's not particularly challenging. Option 2, stencil S1. That's how this looks. Still some upwind bias. Obviously still needs to contain I, but maybe we can add some points to the right. And you would have the corresponding expression here, d phi dx I, comma 1 is equal to 1 over delta x, and the coefficients would be minus 1/6, plus 5/6, plus 1/3. I didn't want to write them, and now I don't feel like leave this thing incomplete. I minus 2, delta plus I minus 1, delta plus phi I. And then the last stencil is the S2 stencil. This is the last stencil that gives you 4 points with still some amount of upwinding. So now we're going to use I minus 1, I plus 1, and I plus 2. And it should be clear that this is the last stencil that we can use, because the next one up would contain I, but would contain absolutely no information coming from the left. There would be absolutely zero upwinding. And here again, we can write the coefficients. No, not plus, minus 1/6. All right, so those are the various options. And now the question would be, we can now let the ENO process follow naturally now. We have 3 options. They're all valid upwinded options. Now the question that we have to answer as an ENO-based computational scientist is, which of these 3 stencils is the smoothest? Okay? And so ultimately you'll collect all this in the following form. In order to get your I derivative with an upwind bias, so the one that goes more from the left, so the minus value, you can take either one of those 3 possibilities, either this guy, or this guy, or this guy, oops, or this guy, and the decision would be based on the smoothness. Okay, so I'm not going to go back and put all the tests, but the test would be if S0 is smoothest, if S1 is smoothest, and if S2 is smoothest. Okay? Now, that gives us the full discretization if A is larger than 0. If we go back up here and we say the flow of information is from right to left, then we have to go through the same thing but the other way around. We've done only half the work. Then you need a downwind, or you need again, the upwind bias would mean a right bias. You would have, again, 3 stencils. You would have the stencil that uses I plus 1, I plus 2, I plus 3. You would have the one that uses I plus 2, I plus 1, I, and I minus 1. And you would have the one that uses I plus 1, I minus 1, I minus 2. You would go through the same thing. Essentially, you would need to flip all the indices and flip the coefficients, and this would be the same story. All right. That's essentially all we need to do in order to do we know. This gives us a scheme that will have third-order accuracy and a sufficient amount of diffusion to avoid oscillations. This is not what we're using in the code. I'm using one more level of complexity on top of that. The observation for this, so let me conclude that by saying, now use same approach for a less than 0, combine, done. So that's your ENO scheme. We'll take one step further. We'll talk now about we know schemes. So a we know scheme is a, depending on your perspective, an improved or an overly complicated version of ENO. ENO, all this is pretty simple. It's tedious, I agree, and we've only looked at the third order. Imagine writing a fifth order or seventh order. It's painful, but the process is simple. We know starts from the following observation. Look at those three beautiful stencils. ENO simply picks one of the three. But we've had, in order to decide which of these is the smoothest, we've had to access all three stencils already. We've done manipulations already on all that data. So we've already worked from I minus 3 to I plus 2. Why not just make use of the data from these three stencils? Well, the reason in the first place is because it is not necessarily smooth enough. But ENO has a very hardcore way of dealing with that. It says, well, if the data is not the smoothest, then I shouldn't use it. We know relaxes that a little bit by saying, well, if the data is not the smoothest, I probably should not use as much of it. So the W in we know is weighted. It's going to be essentially saying, we're going to do that, and that, and that, but then we'll decide how much of each we're using. Why do we do that? Well, because ideally, if we allow ourselves to use freely as much of this, this, and this as we want, then we could optimally use a true stencil going from I minus 3 to I plus 2, which would give us 1, 2, 3, 4, 5, 6 points, which should give us formally fifth order accuracy for our gradient. So basically, if you're in a situation where pretty much everything is smooth enough, you should have readily available a fifth order accurate solution to your problem. It's only in regions where the smoothness of one of those stencils or two of them might become really bad that you really need to move away from this fifth order accuracy and go back down to third order accuracy. So we know does that. How? Well, it's a little bit of magic, and I kind of mean that. So let me just say this stands for weighted ENO. So the idea, why not use all three ENO stencils if the data is smooth? Then fifth order accuracy is possible. So or not if, I should say, in smooth regions, use all stencils. And we're going to combine them as follows. We're going to say that our derivative of our function in x at location I, we're still working with the left bias, right? So it's still the minus. We can do the same thing with the plus one. We're going to simply linearly combine them. We're going to have a weight for stencil 0 that will apply to, well, stencil 0. Plus a weight for stencil 1 that will apply to stencil 1. Plus a weight for stencil 2 that will apply to stencil 2. So that's the idea. Obviously, we still need to estimate the gradient. So it is required for us that omega 0 plus omega 1 plus omega 2 should sum up to 1, or else we're not predicting a gradient anymore. What should the weights be? Well, you can crunch your Taylor tables and figure out what the weights should be, and it's easy to obtain. The optimal fifth order stencil is obtained if omega 0 is equal to 0.1, omega 1 is equal to 0.6, and omega 2 is equal to 0.3. And under those conditions, everything works beautifully. Now, if you're not in a smooth region, fine. In non-smooth regions, the weights go to 0 or 1 to give back Eno. Okay, so one of them will go to 1, the others will go to 0, and we'll get back to our Eno. So this is where I referred. So the question then is how? Well, you need for that to choose an omega 1, 0, 1, and 2 expression. And the way you do this is, I would argue, more an art than a science at this point. So setting up a function that has the right behavior and gives you the proper transition from high order accuracy to highly diffusive. You know, you put something in and you try it out and you see the behavior. But there's lots and lots of different papers that propose solutions to this. One of them I've included in your course pack, that's the Jiang and Peng paper that proposes one way of doing this. Okay. I'm not going to go through the detail of the process. I will just say, I'll give some high-level information on how the weights are calculated. The weights will also be based on the smoothness. So in fact, the weights are going to be based on the leading order terms of the Taylor series that are not going to be included by each of the stencils. So you can estimate them for those different stables that we've built, all those delta of delta of delta. From that information, you can generate coefficients that characterize the local smoothness of the function. Well, then you're going to write a nonlinear combination of those smoothness expressions, such that if your local stencil is very smooth in comparison to the others, such that your weights goes to 1, and such that if your stencil is smooth and the others are also pretty smooth, your weight goes to your optimal weight. So, and this takes the form of essentially ratios of smoothness calculations, your own smoothness versus the average smoothness of the other stencils. It looks pretty ugly, and I'll just show you how it's implemented in the code, but we're not going to do much more of that. Because you're kind of smoothly, in a hand-wavy way, transitioning from high order to more upwinded behaviors, you're going to tend to see a more oscillatory behavior of Reno schemes. They tend to be more accurate and less dissipative, less diffusive than Eno, but they tend to be less robust than Eno. Let me see. We also observed that the CFL restrictions associated with Eno and Reno, they tend to be pretty strict. The effective CFL to maintain the non-oscillatory behavior is not obvious to find, but the CFL for stability, you can derive the CFL for non-oscillatory behavior. It's typically pretty low, on the order of a fraction of unity. All right, I have a few more notes on this, but I think we spent already an enormous amount of time on that, and I want to talk about the rest of the code. Any questions on Eno, Reno? You see how we build all this? It's reasonably clear. So you can see this. Yes, go ahead. How is this what?
Smoothness, how to decide which.
Oh, well, this is what we wrote right here.
How to decide which one is smooth?
So it's a combination of tests like this.
Will be incorporated in.
Yes, so let me write it down exactly. So whether your stencil has grown left or right is a simple question of whether this or this is larger. And then whether your additional point is further left or further right is a question of whether this or this is larger. And then whether your last point is further to the left or further to the right is a question of a delta, delta, delta test. So you can summarize this easily because we know that in any case, because of our upwind bias here, we know that the three stencils we have, they both contain I-1 and I. So one of the tests, the first level test, as to whether that difference or that difference is the least, that we don't need to do because we know that we always want to have that difference in all three stencils. So the only question for us is the difference between this and this less than the difference between this and this? And then the difference between this and this less than the difference between this and this. So let me write this down explicitly this way. Hopefully this will be clear. So right here, under which condition do we use this? Well, we will use this if we've decided to add the point to the left. That means that the minus difference of the first difference is less than the plus difference. So that will take this form. The delta minus of the delta plus, excuse me, of phi I minus 1 should be less. That's not a less, that's a bar. It's less than the delta plus, the delta minus of the delta plus of phi sub I. And the second test is delta minus of delta plus of phi sub I minus 1 should be less than the delta plus of the delta minus of the delta plus of the phi sub I minus 1, I think. I might have a typo here. This is something where you would have to go back to the paper to check this. But essentially, this is the combination into one simple test of what we wrote up here, of this process of do we add the point to the left or the point to the right. So the series of positive negative tests that lead to that stencil is what you would end up checking for when you pick stencil 1, which I think, if I copied that correctly, I think this is this test. And then you can do the same thing for S1, same thing for S2. Do you see where this comes from? Yeah. Other questions? So it is very much customary in level set schemes to make use of fifth order Wieners. Those are very much the de facto standard. Third order TVD Runge-Kudus combined with fifth order Wieners are kind of the reference methodology for level set advection and reinitialization. So this is, you can see that there's a lot here. To simplify our life a little bit for the code, I moved away from the third order Runge-Kudus. This is not a big simplification. We're just going to do first order forward Euler. But the second bigger simplification is that we're going to limit ourselves to that stencil. Okay, so to a third order Wiener. Well, to a third order Eno, but upgraded to Wiener. So you'll see the weights in the code. All right, ready to unplug and move to the computer? Okay. There we go. All right. So let me close this. So we'll take a look at the code first. So we're going to move to the second directory. Oh, that's not what I wanted to do. So all we're going to do is we're going to look at the same stagnation flow, and we're going to make sure that our gradient doesn't go crazy. Okay, that's it. But before we do that, I'll show you. So this is the same environment, the same stagnation code, stagnation flow, the same planar interface. Let's take a quick look at the code. There's one thing that I did not mention when I talked about the level set reinitialization that I'll mention live as we look at the code. So I have two parameters for my reinitialization. One is the maximum number of reinitialization steps. I told you that in the end it's reasonable to do on the order of 5 or so, or the few to maybe 10 or so. So here, to be safe, I put 10. So I'm not going to use as an exit criterion anything related to the error. I'm going to use as an exit criterion the amount of work that I've expended in this. I'm adding one more thing here, which is the fact that in a general sense, you only need to reinitialize as much as needed to maintain a reasonable gradient. Well, if you run at a limited CFL for advection, your kinematic the kinematics of the flow are not in a position to change drastically the gradient from one time step to the next. You need to let the flow distort the level set over a certain amount of time in order to have an actual gradient to fix, to reset. So I'm not reinitializing at every time step because the cost would be enormous. So I'm doing 10 time steps of my reinitialization, which is literally 10 times the cost of one step of level set transport. So I've already increased 10-fold my cost. But now I'm going to reduce by another factor of 10 by saying, well, I can probably wait safely about 10 iterations before I do this reinitialization. So overall, the cost will be, on average, of one reinitialization step per time step, on average. I don't do it like that. I do 10 steps at a time every 10 steps. But that means that my reinitialization equation now represents essentially a factor of 2 in the cost of my level set scheme, no longer a factor of 10 or 50. Okay? And the question for us is the resulting flow field, not flow field, but level set field, does it look reasonable? In a general sense, it will not look reasonable far from the interface. But hopefully, within a few cells of our interface, it should look like a proper distance field. Okay? Further away, our information will not have traveled far enough. Our reinitialization information will not have traveled far enough to influence the faraway regions. But those don't matter. Okay, this is my initialization. There's nothing of interest here. This is my step. This is my level set equation update done with Adam Bashforth. I'm applying normal conditions. Then I'm computing normal and curvature. Nothing new. This is where I do my reinitialization. This is simple. This is an if if it's been 10 steps since my last reinitialization, or basically if my number of time steps is divisible by 10, then I call my level set reinit. So now that it's level set reinit, you can see that this is, well, there's some code in it. First, let us check one simple thing. I'll go in here and comment out, whoops. Let me try again. I will go in here and comment out everything here, and I will instead show what happens if you compute naively this whole thing. Okay, this is dg/dx. According to how we compute our normal vector, it's the same thing centered gradient. dg/dy. I take the normal, the square root of the sum of the square. That's the magnitude of the gradient, and I compute I compute essentially 1 minus the norm times the sign of my initial field, my initial level set field. Well, you can see it's so bad it doesn't even compile. So I need to uncomment this and go again. So it runs. Let's take a look. Okay, so I'll create my cut plane through the middle. So remember, I think this case here, we were seeing the gradient go down, 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 and then essentially we had just a 0 level set. So this is what we're hoping to fix. Wow, that was quick. Well, that's a bit underwhelming. I don't know if you can see, but my range goes from minus nan to nan. So this is just not a number right away. So it's not a very, I don't remember how I visualized this to make it obvious that this was not working. But I think not a number in your answer is probably a reasonably convincing reason to not use this discretization. So in the interest of time, I'm not going to spend more time on this. So, I don't need to quit. So hopefully this is convincing enough. If not, let me know. We can play with this some more. But yeah, it just doesn't work if you do centered differentiation. So let's look at the code now. What we're going to do is we're going to first prepare our we know coefficients. The we know scheme by definition needs to know what the data is like in order to decide how it's going to discretize the gradient. So at each time step, we need to build on the fly what the scheme is going to look like. Then once we have our scheme, which is this we know that I'm storing here, I have this we know 3 underscore xm, and I have the xp. So I have the minus tensor and the plus tensor. The minus tensor is a combination of the 3 enos tensors we've talked about. The plus tensor is the combination of the 3 right-biased enos tensors that we didn't write but are equivalent. And same thing in y. This is just the application of the product between the stencil and my local set of points. You can see that this indeed is upwind bias. It goes from -2 to +1. And that gives me my minus derivative, this gives me my plus derivative in x, that is my minus derivative in y and plus derivatives in y. Okay? So those are the A, B, C, and D coefficients that, that Sussman introduced for the calculation of his good enough flux. Okay, so this is just my left bias, right bias, bottom bias, top bias derivatives. From that, I need to plug all this into the calculation of a good enough gradient. The expression is exactly the one we wrote, as is. In fact, I looked at the same notes to type it up because I certainly don't know it by heart. So we took the max of the, so here we needed A plus. A plus is the positive side of this. So if this gradient is positive, we'll take it. If it's negative, we'll set it to 0. And then we square it. And then we need the plus. So we need the right biased, the right biased derivative. If it is negative, we use it. If it is positive, we set it to 0. We square it. I'm going to sneeze. Oh, maybe not. I guess not. I guess not. And then same thing in y. Take the square root. That's my the solution I get if my flow of information is in the positive space direction, meaning if my phi is more than 0. If my phi is less than 0, I have the second expression, which gives me this. So this is, again, a direct implementation of what we wrote. Then we had this, this sine function. This is the implementation of the sine function that I have here. This is based on the old value. By the way, I should have shown. Where is this old value coming from? This old value is just storing the value I get into the reinitialization code with. So I've just obtained my new g at my time. I will remember this in the g old value so that I can compute my sine. In fact, I could have stored my sine here and recompute it at every step of my reinitialization. I wouldn't need to do that. That would save me some time. And remember, we said this needs to be the ratio of the phi naught over the absolute value of phi naught. Therefore, the ratio of phi naught to the square root value of the square root of the square of phi naught. But then if phi naught is 0, I need to fix this. I add an epsilon that's exactly like Sussman. This epsilon is chosen to be the mesh size. And then in a general sense, you want to be careful. I don't like divide. Well, I just added the value here following the paper of Zhang and Peng, because your mesh size will become smaller and smaller. And at some point, you want to make sure that things remain well behaved. So if you conduct mesh refinement, it could be useful. And finally, we assemble everything. If the sine is more than 0, I use the g plus. If the sine is less than 0, I use the g minus. And don't forget, the reinitialization is the good enough gradient minus 1. So the goal is for the gradient to become ultimately equal to 1. I integrate way faster than Sussman. Sussman was using a fifth order winnow. I use a third order winnow. As you decrease the accuracy of your schemes, you usually are in a position to increase the CFL at which you run. The CFL, I said, was set by D. Here I'm going to use 0.75 times D. So I have some safety margin, but not enormous. And then I just do first order forward Euler. I do g is equal to g plus dt times dg dt. That's it. All this is encapsulated in a loop over that goes from 1 to the maximum number of reinitialization steps that I've prescribed, which is 10. Okay, I think that's it. I update Neumann conditions at the wall. Oh no, well, there's the winnow. Let me show you the winnow. So this call here sets my local winnow for my points. Well, we talked about how this works. This is this thing. It's not that complicated, but it's been compressed over the years. This is where I compute some ratio of the smoothness, essentially, that allows me to set the weights. This is, again, compressed as much as possible. The coefficients are set. Let me think. What am I? Yeah, it's amazingly compressed. I'm trying to now remember where Yeah, okay, so the stencil is, so we end up, you end up being in a position to write, you don't need to write the 3 weights. There's 3 stencils, therefore there's 3 weights. You don't need to write the 3 weights because the third weight you can obtain by doing 1 minus the sum of the 2 other weights. So you only need to keep track of 2 weights. This is this weight minus and this weight plus. So those are those 2 weights. And then you need and then basically everything has been simplified. The ENO coefficients have been embedded in this. Everything that can be simplified has been simplified, and that ends up boiling down to this fairly simple expression. So this is my left bias stencil in X. This is my right bias stencil in X. And then exactly the same thing in Y. Again, this is done on the fly. What I do is I specify to that little routine, or that little routine, in fact, just directly looks at the ij where it sits, and it probes the local data at I minus 1, I minus 2, I plus 1, I plus 2, j minus 1, j minus 2, j plus 1, j plus 2, and it looks at the local smoothness, it combines all this, and it returns directly the plus and minus coefficients to be used in both directions. Okay, any questions on this? Does it seem reasonable? Okay, so hearing no comments, let us try this. So remember, we were compressing our profile or stretching our profile such that the gradient was going to infinity or to 0. The hope here is that no matter how long we're integrating, gradient should remain 1, at least in the neighborhood of the interface. So first of all, this thing ran in a few seconds, maybe 2 or 3, maybe 5 seconds before. Now the cost has increased significantly. It took us 20.5 seconds. I don't remember how long it took before, but I think it took less time than this. So let me reopen this. We'll just confirm that that we maintain control over our gradient. So this is our initial G. And now you can see, as time goes by, there's some adjustment initially, but extremely minor. This is a boring plot to show you, really. But you know, there was a lot of work associated with getting that boring plot. So the fact that this thing does nothing, it just has some very minor adjustment, that got me excited at least. So in the interest of time, we're not going to do the other case. So this was the compression case. We can do the other case. I don't even know which one this was. This was X, I think. Oh, this is Y. So yeah, this is the compression case. So you can see that we're able to counteract the compression of the interface. We could do the exact opposite thing and check that the same way things remain the same, but they will. So we're not going to worry more about this, except if there's any questions. But you know, feel free to play with it as much as you want. Now we're going to look at the consequences. So you know, by the way, yesterday we played with the Zelizac and the deformation problem, but we didn't really do much with it. Beyond just observe that things were working reasonably well. There were some numerical errors, but nothing too bad. Now we're solving a second equation on top of the first one. So let's revisit our initial problem and redo the Zelizac problem now with this reinitialization equation. The main consequence that would be observable at this time for this Zelizac notch disk rotation is the fact that the cost has increased. But then, so if you go to the third directory and take a look at, run it and take a look at what's going on, So this is our G field. I will create again the velocity vectors at a lower density than this. So we're rotating this thing. Let us look at the isosurface of G is equal to 0. All right. So it would be good to, what I would encourage you to do is pull up the previous the solution that we had. And I'll do that quickly. So Insight in general is capable of looking at two data sets simultaneously, but in this specific situation, because we're using the free version, it is not. So we need to open up a second Insight window to do this. All right. This is the old one. And this is the new one. So I'll let you make your own opinions with this, but so this is the old one where we didn't have reinitialization. This is the one with reinitialization. Reinitialization was, so it adds to the expense. So we made this, the case that this is a necessary step in our algorithm, okay? But it adds to the expense. It degrades the quality of the solution. It should be reasonably clear that this notch has kind of deformed within the disk. And it also, I don't know how obvious it is, but I think the corners have become a little bit more rounded than they were before. And that would be expected because we're solving yet another equation that will have numerical errors that will be diffusive in nature to the leading order for stability. So that should, the message for this test case is the following. Reinitialization is an unfortunate, it's a need for us, unfortunately, but it's really a necessary evil. This is an extra cost, it is a painful equation to put in, and the outcome is a worsened performance. And this is not one of those feel-good stories where we add this equation and suddenly everything looks much better. No, systematically removing reinitialization in test cases will help you achieve better results. But in any type of serious production runs, if you don't have reinitialization, your code will crash. So you need to do something like that, but you pay the price by effectively reducing the accuracy of your method. Okay? One of the things we could do with this is vary the mesh resolution and start to see what happens if instead of having about 10 cells across this structure, what happens if we have only a few, like 2 or 3. And then you can start to see how bad things can get in terms of following fairly thin structures. We're not going to do that in the interest of time. We started late already. I'd like to finish on time, so we'll just leave it at that, except if there are any questions on this. So you get the message, right? The message is we spent a lot of time, played with a lot of equations, added lots of lines of code, and the result is that, well, we should all be disappointed, but that's life. Okay. The last case for us to wrap this up is the, oh, that's not what I wanted to be, is the deformation test case. So we're going to go through the same exact exercise. You know, so this is the same disk being stretched in the vertical flow for 4 time units until maximum stretching and then being pulled back. Nine seconds of runtime. With reinitialization, without reinitialization, it takes 5 seconds. We estimated that we should have about a factor of 2 in time because every 10 steps of our transport equation, we perform 10 steps of our reinitialization equation. That's kind of what we're seeing. This corresponds to the expectations. Okay, so to wrap up our story, let's look at this guy. So there should be no expectation of a significantly different behavior compared to what we showed before, but we'll make a few things more obvious. It becomes absolutely obvious here that we are reinitializing our distance PDE. Right? We have now a distance at all times. Right? You can see that, and in fact, the best way to see that would be to add isocontours of G. If I add isocontours of G between minus 0.5 and, 0.05, what? Oh, a plus would help. You can see that those isocontours are truly remaining equidistant throughout our entire shape here. Okay? So we are truly solving here a redistancing algorithm. Let me hide these and pull up at the same time what our field looked like without reinitialization. Is everyone getting reasonably familiarized at this point with Insight? Yeah, things are. Because I've kind of stopped telling you how I do things, so I'm assuming that you're managing to follow somehow. So let us create our isocontour at 0 here. I'll put it in black. And we will go from minus 0.5 to let's go to minus 0.5, like I said, to 0.5. All right. So this is our old results, and our new results, we're going to do the same thing as far as the palette is going to go. We're going to go from minus 0.5 to 0.5. Well, maybe we should go to minus 0.1 to 0.1. Okay. Let's be consistent. Minus 0.1 to 0.1. There we go. Those are at the same time. 0.4. So 4 time units, 4 time units. So what's happened? Well, this thing predicted a much thinner structures. It was capable of representing a much thinner structure. But the reinitialization equation doesn't let us go to that small structure. The reason for that is because our sign distance, our sign function in the distance reinitialization equation has a certain length scale in it that's tied to the mesh. So we will end up preventing essentially the formation of essentially one cell thick ligaments like we had here. A transport doesn't care. A transport doesn't know anything about the interface. It doesn't know anything about the zero isosurface. So whatever happens to it, happens to it. The reinitialization equation knows about it, and it changes in nature as you get very close to that value, because this is how we would transition from a positive sign to a negative sign. So there's some good that's happened here. All this stuff here, so remember I said that the exact solution should be a ligament that extends to about here. Well, the length of the ligament that we capture in this thing has extended quite a bit. So we've been able to maintain this ligament, but we've done that by artificially thickening that ligament according to this reinitialization equation. So one thing that should become pretty obvious here, we defined our sign function with in mind this rule that ideally we don't touch ever the zero isosurface position. Right? That's the entire idea. If you change the position of the zero isosurface, you're messing up your physics. Well, just simple examination of the interface position shows you that we have changed the zero isosurface location. We've moved this back a little bit and move this back as well. So our reinitialization equation, again, is going to be, okay, it gives us a very nice, good-looking field, but the price we have to pay is we've messed up the physics of transport. By all intents and purposes, this was more accurate than this as far as position was represented. Let's go to the final time, and then we'll look at the curvature field. Both looked like potatoes, but this is an okay potato. This is a pretty terrible potato. So again, level set. Reinitialization is a necessary evil, but it's absolutely an evil thing. Let me go back here and show our distribution of curvatures. I should have thought more carefully about the appropriate range before showing you this. We'll try minus 20 to 30, and we'll do the same thing here. The curvature, there isn't too much to say. That was weird. The curvature, there isn't too much to say here, apart from the fact that our field here, away from the interface, contained a lot of again, the derivatives were pretty complex, and they came from the transport of our field away from the phi is equal to 0 value. So we had lots of information far here that our reinitialization has essentially taken care of. We don't have any of that anymore. The curvature wasn't that bad when we were looking at it from the non-reinitialized configuration. So this didn't look that bad. We had a negative curvature in that area, a positive curvature on the other side, which is what we would expect. The same is true here. We have the same situation of going from a negative curvature to a positive curvature. Both of these fields look okay as far as the near interface values are concerned. Everything else further away, it doesn't matter to us. We're never going to use it. Should point out that it's kind of nice to see that we properly pick up the high curvature regions right here. So those are regions of high positive curvature. Okay, so we have now a reinitialized level set solver that is capable of telling us the normal orientation of the interface as well as the local curvature of our flow field. Tomorrow, I can't remember, so I'll check, but we either look at VOF or we continue and finish the level set by coupling with the flow solver. So let me take a quick look. So tomorrow we are finishing up our level set code. So what we'll do now is we'll fully couple that with the flow solver. There isn't that much that needs to be done. And in fact, we talked about it pretty extensively for the first hour or so of the lecture this morning. So we need to set the density, the correct density where we need. We need the correct viscosity. And we need to also use something like a gauge fluid method or an end-cell reconstruction technique, because we've been we've used more of a finite difference perspective to dealing with the level set. We'll use a gauge fluid technique tomorrow. Okay, so we'll fully implement the gauge fluid, and then we'll play with dancing bubbles. All right, thank you for your attention, and we'll continue tomorrow.